Good morning everyone. I am Garima from Basic Chemistry Honors first year. Today we are going to start our chapter cycloalkanes from Organic Chemistry. Introduction. Cyclic alphabetic hydrocarbons or alicyclic hydrocarbons are hydrocarbons which contain closed chain or rings of carbon atom and resemble open chain or aliphatic hydrocarbon in many respects. Like aliphatic hydrocarbon, acyclic hydrocarbons may be saturated or unsaturated in nature. Saturated acyclic hydrocarbons are generally known as cycloalkanes. They have the general formula CnH2n and are isomeric with alkenes. In this chapter, we shall discuss the chemistry of cycloalkanes, nomenclature of cycloalkanes. Common names. Saturated acyclic hydrocarbons contain a number of methylene groups joined together to form a ring. Therefore, they are known as polymethylene in common system. Accordingly, the individual members are named by prefixing the number of carbon atom in the ring before the word methylene. For example, trimethylene, tetramethylene, hexamethylene. IUPAC name. In the IUPAC system, the saturated alicyclic hydrocarbons are termed cycloalkenes. The individual members are named by adding the prefix cyclo to the name of corresponding straight chain hydrocarbons having the same number of carbon atom as the ring. For instance, cyclopropane, cyclobutane, cyclohexane. Quite often, alicyclic hydrocarbons are also represented by drawing simple geometric figures such as a triangle for cyclopropane, a square for cyclobutane, a pentagon for cyclopentane, and so on. The presence of carbon atom at each of the corner and hydrogen atom attached to carbon is taken for granted. For example, cyclopropane is shown as a triangle as shown in the figure, cyclobutane, cyclopentane and cyclohexane. Nomenclature of substituted cycloalkanes. IUPAC name of substituted cycloalkane are assigned by following the IUPAC rules which the students have already studied. However, some important points are given below. First, for mono substituted cycloalkanes, there is no need of numbering to indicate the position of group. For example, methyl cyclohexane. For cycloalkane containing more than one substituent, the numbering of the carbon atom of the ring is done in such a way that the substituent get the lowest possible number. Their names are prefixed in alphabetical order along with their position. Moreover, the substituent which come first in alphabetical order is given the lowest possible number provided it does not violate the lower set of locant rule. For example, 1,3-dimethyl cyclopentane, 4-ethyl 1,2-dimethyl cyclohexane, 1-ethyl 2-methyl cyclopentane. If the ring contain equal or more number of carbon atom than the alkyl group attached to it, the compound is named as a derivative of cycloalkane and the alkyl group is taken as the substituent as already shown above. If the ring contains lesser number of carbon atom than the alkyl group attached to it, or if more than one ring is attached to a single ring, the compound is named as a derivative of alkane and the alicyclic ring is treated as the substituent. For example, 2-methyl 1-cyclopropyl butane, 1,3-dicyclohexyl propane. In addition to the above rule for cycloalkane, some important points for naming cyclo compounds containing multiple bonds or other functional groups are given below. First, if the carbon atom attached to the alicyclic ring contain a multiple bond or a functional group, the carbon chain is taken as the parent and the ring is treated as the substituent irrespective of the size of the ring. For example, 3-methyl 1-cyclobutyl but 1-in 1-cyclohexyl but 2-in. If the compound contain a alicyclic ring directly attached to the benzene ring, it is named as a derivative of benzene. For example, cyclohexyl benzene 1,3-methyl cyclohexyl 4-nitrobenzene. This 3-methyl cyclohexyl is attached on the first position, so it is shown in the bracket. If the ring contain a multiple bond and the side chain contain a functional group, the ring is treated as a substituent and compound is named as a derivative of the ring containing the functional group. For example, 4-cyclohex 2-enyl butane 1-ol. If the functional group contain carbon is directly attached to alicyclic ring, the carbon of this group is suitably included in the suffix used for the group. For example, CHO group is represented by the suffix carbaldehyde, C double bond OH by carboxylic acid, and CN by carbonitrile. These are the examples: cyclopentane, carboxylaldehyde, cyclohexane, carboxylic acid. Synthesis of cycloalkanes and their derivative only method number 3, 5, 7 are included in the syllabus. The important method of synthesis of cycloalkane and their derivative are described below. Most of these methods, it may be noted, involve the conversion of some open chain compound into a cyclic compound through the process of cyclization or ring closure. The cyclic compound thus obtained may be a cycloalkane or its derivative if required. The cycloalkane derivative is further subjected to suitable reaction to change it into the desired cycloalkane itself. First, addition of carbene to alkene. The method involves the addition of carbene to alkene to form cyclopropane derivative. The reaction is also referred to as cycloaddition. Since free carbenes are too reactive to be isolated, the reaction is actually carried out by using a carbene precursor that generates the carbene under suitable experimental condition. For example, when treated with diazomethane or ketene in the presence of light, alkene add on carbene to form cyclopropane derivative as shown in this reaction. For instance, 2-butane in the presence of sunlight will give 1,2-dimethyl cyclopropane. Second, Simmons-Smith reaction. In this method, addition of carbene is carried out by treating the alkene with methylene iodine and ZnCu couple to get cyclopropane derivative. For example, ethene plus CH2I2 in the presence of ZnCu will give substituted cyclopropane plus ZnI2. ZnCu couple required for the reaction is usually obtained by heating Zn dust with CuCl in ether in the presence of nitrogen. It is believed that methylene iodine and zinc react to form a carbene-like species called carbenoid. CH2I2 plus ZnCu will give ICH2ZnI. The carbenoid brings about the stereospecific addition of CH2 group directly to the alkene as shown in the reaction. Simmons-Smith reaction give better yield of cycloalkane than is obtained by the addition of a free carbene to the alkene. Third, photochemical 2+2 cycloaddition reaction. The term cycloaddition denotes addition reaction between two unsaturated molecules to form a cyclic product. During this reaction, new sigma bonds are formed at the cost of pi bond of the reacting molecule. Individual reactions are designated by writing the number of pi electron of each reactant in a square bracket. For example, a reaction between two alkene molecules to form a cyclobutane ring by using 2 pi electron of each molecule is referred to as 2+2 cycloaddition. 2+2 cycloaddition reaction can be carried out easily in the presence of light but not under thermal condition. Such reactions are termed as photochemical 2+2 addition cycloaddition reaction. They takes place by a concerned mechanism involving cyclic transition state. The formation of substituted cyclobutane by photochemical 2+2 cycloaddition of two alkene molecules may be represented in general as follows. Alkene 2 molecules in the presence of sunlight will give cyclic transition state, which will further give substituted cyclobutane. For example, CH2 double bond CH2 plus CH2 double bond CH2 in the presence of sunlight will give cyclobutane. Fourth, 4+2 cycloaddition Diels-Alder reaction. 4+2 cycloaddition reaction involve the addition of a alkene that is 2 pi electron referred to as dienophile and a conjugated diene that is a 4 pi electron to form 6-membered system. In contrast to 2+2 cycloaddition, these reaction takes place readily under thermal condition. For example, 1,3-butadiene diene ethene dienophile 473 Kelvin temperature will give cyclohexane. If the dienophile contains electron attracting groups such as C double bond OH, CO, C and Cl, the reaction takes place extremely easily and sometimes even at room temperature. For example, 1,3-butadiene plus CHOCH double bond CH2 in the presence of 373 Kelvin temperature will give 1236 tetrahydrobenzaldehyde. It is interesting to note that 2+2 cycloaddition reaction takes place readily photochemically but not thermally. On the other hand, 4+2 cycloaddition reaction occurs readily thermally but not photochemically. Fifth, dehalogenation of suitable dihalose derivative of alkanes. Freund's method. On treating of suitable sigma dihalosine derivative of alkane, that is dihalosine derivative having the halosine atom attached to terminal carbon atom with sodium or zinc, they get dehalogenated to form cycloalkanes. For example, 1,3-dibromopropane plus zinc will give cyclopropane plus ZnBr2. 1,4-dibromobutane plus Zn will give cyclobutane plus ZnBr2. This method may be regarded as the internal Wurtz reaction. However, this method gives good yield only in the preparation of cyclopropane. If the sigma and gamma dihalide contain more than 6 carbon atom, intermolecular Wurtz reaction takes place, giving rise to open chain Dickmann cyclization. When ester of certain dicarboxylic acid such as adipic acid and pimlic acid are treated with sodium or sodium ethoxide, they undergo intermolecular condensation to yield cyclic beta ketoesters. The beta ketoesters on hydrolysis and heating get decarboxylized to form cyclic ketones. The ketones are in turn subjected to Clemenson reduction to get cyclic alkanes. For instance, aliphic ester on treating with sodium will give 2 carboethoxycyclopentanone, which on hydrolysis will give 2-carboxyl cyclopentanone, and cyclopentanone on treated with zinc, mercury, and HCl will give cyclopentane. Dickman method is most suited to the preparation of 5 and 6 membered ring. 7. Pyrolysis of calcium or barium salts of dicarboxylic acid. When the calcium or barium salt of certain dicarboxylic acid are heated strongly, they yield a cyclic ketone. The ketone thus formed is converted into cycloalkane through Clemenson reduction as illustrated below. Calcium adipate in the presence of heat will give cyclopentanone. On treated with zinc, mercury, HCl will give cyclopentane. In keeping with Black's rule given below, this method is used for the preparation of 5 and 6 membered ring ketones. Blake's rule. This rule was formulated by Blake's on the basis of experimental observation of ease of formation of cyclic anhydride and ketone by distillation of dicarboxylic acid according to relative position of a 2-carboxylic group. According to this rule, distillation of 1,4 and 1,5 dicarboxylic acid gives rise to cyclic anhydride, while 1,6 and 1,7 dicarboxylic acid yield ketones. 1,8 and higher dicarboxylic acid remain unaffected. Black's rule can be used for determining the size of ring as well as the chain length of dicarboxylic acid. For this purpose, a double bond is introduced by suitable method in the given compound whose ring size is to be determined. The unsaturated compound thus obtained is subjected to oxidative. There is no change. The acid is 1,8 or higher. The structure of the acid in turn reveals the size of the ring. 8th. Thorpe-Ziegler reaction. On heating in the presence of lithium diethylamide C2H5 twice N negative Li positive and alpha gamma dinitrile, that is a dinitrile in which nitrile group are attached to terminal carbon atom, undergo intermolecular condensation to form a cyclic aminonitrile. This is changed into cycloalkane as illustrated below. Alpha gamma dinitrile in the presence of C2H5 twice and negative Li positive will give aminonitrile, which on hydrolysis will give keto acid, which on treated with heat will give ketone, and it further treated will give ZnHg, and HCl will give cycloalkane. The first step in the reaction involving cyclization takes place only at very high distillation. It is referred to as Ziegler high dilute technique. Thorpe-Ziegler reaction is particularly suitable for the preparation of higher ring compounds. 9th. Dimjanov rearrangement. The reaction provides a method of expanding and contracting alicyclic ring system through the formation of carbocation. The carbocation themselves are obtained by the deamidation of alicyclic amines by treating with nitrous acid. Once formed, the carbocation undergoes its characteristic reaction, that is, first addition of nucleophile, elimination of a proton, rearrangement to a more suitable carbocation. As a result, different products are formed, including ring expansion on ring contraction products as illustrated below. 10th, hydrogenation of aromatic compounds. Cyclohexane and its derivative can also be prepared by the hydrogenation of benzene and its derivative. For example, benzene plus 3H2O in the presence of nickel and 423 to 473 Kelvin temperature will give cyclohexane. 11th, condensation of suitable dihalides with malloic ester or acetoacetic ester followed by hydrolysis and decarboxylation in the presence of sodium ethoxide. Active methylene compounds such as malonic ester and acetoester condense with suitable dihalide to form cyclic diesters. These on hydrolysis and decarboxylation yield cycloalkane. For instance, ethylene dibromide and malonic ester plus 2C2H5ONa will give cyclopropane and dicarboxylic ester on hydrolysis will give cyclopropane dicarboxylic acid. On heating, it will give cyclopropane monocarboxylic acid. Cyclopropane monocarboxylic acid is then converted into cyclopropane through a scheme of reaction. It may be noted that this acid cannot be directly decarboxylated by heating as it led to cleavage of the ring. Acetoacetic ester may also be used in the place of malonic ester in this reaction. For example, as shown in this figure, the ketone obtained above is suitably treated to get the corresponding hydrocarbon. 4.15 Physical properties. First, in their physical properties, cycloalkane resemble the corresponding open chain compounds, although they have somewhat higher boiling point and densities. For instance, the first two members of cycloalkane, cyclopropane and cyclobutane, are gases while higher are liquids. They are non-polar in nature and as such insoluble in water but soluble in organic solvents. Some of them, such as cyclohexane, are good solvent themselves. 4.16 Chemical properties. The general chemical behavior of cycloalkane is similar to that of corresponding open chain hydrocarbon like alkane. Cycloalkane also contain only carbon-carbon and carbon-hydrogen single bond and are therefore quite inert towards chemical reagent and undergoes only a few substitution reaction. It may be emphasized, however, that cyclopropane and cyclobutane differ considerably from their higher homologues. This is because the cyclopropane and cyclobutane rings are not very stable and have a tendency to open up and form addition products, as explained in session 4.17.1. As such, they resemble alkenes in undergoing some addition reaction, but they are less reactive than corresponding alkenes. A few reactions of cycloalkanes are described below. First, reaction with halogen. Generally speaking, cycloalkane undergo free radical substitution with halogen at high temperature or in the presence of light. For example, cyclohexane plus Br2 in the presence of sunlight will give bromocyclohexane plus HBr, and cyclopropane plus Cl2 in the presence of sunlight will give chlorocyclopropane. In case of cyclopropane, however, bromine and chlorine breaks the ring system in the presence of FeBr2 or FeCl thrice, and high temperature and yield open chain addition products. For example, cyclopropane plus Br2 in the presence of FeBr3 will give 1,3-dibromopropane. Second, reaction with halogen acid. In general, cycloalkane do not react with halogen acid. However, cyclopropane adds on halogen acid to form open chain alkyl halide. Cyclopropane plus HI will give N-propyl iodide. Cyclopropane plus HBr will give N-propyl bromide. And cyclohexane plus HI will give no reaction. Third, addition of water. When heated with concentrated H2SO4, cyclopropane but not other cycloalkane add on water to form an alcohol. Cyclopropane plus H2O in the presence of H2SO4 will give N-propyl alcohol. Fourth, reaction with halogen. When heated with hydrogen in the presence of nickel, cyclopropanes and cyclobutane form open chain addition product with higher cycloalkanes do not react. Reaction of cyclobutane takes place at much higher temperature than required in the case of cyclopropane. Cyclopropane plus H2 in the presence of nickel 353 to 373 Kelvin will give N-propane. Cyclobutane plus H2 in the presence of high temperature will give butane. Similarly, cyclohexane plus H2O will give no reaction. It may be noted that of the cycloalkane, cyclopropane is the most reactive since it undergoes many addition reactions accompanied by ring cleavage. Next comes cyclobutane, which undergoes addition of hydrogen, while the rest of cycloalkane do in theory. During the earlier stages of their study, cycloalkane containing up to only 6 carbon atom ring could be prepared in the laboratory, and the ring containing 7 or more carbon atom were unknown. It was also observed quite easily that like open chain alkane, cyclopentane and cyclohexane are quite stable and do not undergo addition reaction. On the other hand, cyclopropane and cyclobutane were found to be relatively much less stable and capable of undergoing even addition reaction through ring cleavage. The difference in the relative stability of different cycloalkanes was initially explained in the terms of Bayer strain theory as discussed below. Bayer strain theory. According to tetrahedral concept of carbon, a carbon atom bonded to 4 other carbon atoms lies at the center of the tetrahedron, and the angle between any two bonds is 109 degree 28 second. Adolf von Baer 1885 argued that any departure from this position leads to the strain in the molecule, as a result of which the stability of the molecule decreases. On this basis, Baer proposed a theory known as Bayer's strain theory. The important points of this theory are: first, the carbon atom containing the ring lies in the same plane. Consequently, the bond angle between the adjacent carbon atom of the ring no longer remains 109 degree 28 second, which is the normal bond angle of the tetrahedral carbon. On the other hand, different rings have different values of this angle. For instance, the cyclopropane ring is a triangle having a CCC angle of only 60 degree. Second, any deviation, positive or negative, from the normal tetrahedral bond of 109 degree 28 second during the formation of a ring products an internal strain in the resulting molecule, which makes the molecule unstable. Positive derivation means that the angle is compressed, while negative deviation means that the angle get expand. Third, the greater the derivative from the normal angle, the greater is the strain, and therefore lesser is the stability it may. The more the stability of the ring system, the more easy it is formed. Bayer calculated the deviation from normal angle, or what makes to be called angle strain, involved in the formation of cycloalkane of various ring size. For example, the CCC angle of the cyclopropane ring is 60 degrees since each carbon atom occupies a corner of an equilateral triangle. This means that the angle strain in cyclopropane would be 1 by 2 of 109 degree 28 second minus 60 degree, or 24 degree 44 seconds. Similarly, the CCC angle in cyclobutane is 90 degree as each carbon atom is situated at the corner of a square. As such, the angle strain in cyclobutane is 1 by 2 into 109 degree 28 second minus 90 degree, or 9.9 degree 44 second. The angle strain for cycloalkane of various ring sizes are summed up in the table 4.1. Limitations of Bayer strain theory. Bayer strain theory failed to explain the following. First, ease of formation of ethylenic bond. The ethylenic bond can be formed readily in spite of having such a large angle strain. Second, stability of cyclohexane and higher cycloalkane. Heat of combustion of cycloalkanes. Bayer strain theory failed to explain the stability of cyclohexane and higher cycloalkanes as discussed below. Cyclohexane and higher cycloalkanes, many of which are prepared after Bayer strain has been proposed, are found to be nearly as stable as cyclopentane, as shown by their heat of combustion. The heat of combustion per methylene group CH2 of various cycloalkanes are given in table 4.2. The table 4.2 shows the heat of combustion per CH2 group of cycloalkane. Heat of combustion per CH2 group of open chain alkanes is 658.5 kilojoule per mole. The heat of combustion per CH2 groups gives a fair idea of the relative stability of cycloalkane, since each CH2 group yield only carbon dioxide and water on combustion. If the heat of combustion is large, the compound contains more energy and is therefore less stable, and vice versa. Immediately apart from table 4.2, that as compared to open chain alkane, cyclopropane and cyclobutane give only nearly 38 and 28 kilojoule more energy per CH2 group. This means that they are relatively less stable, a fact which is in agreement with the Bayer strain theory. However, the heat of combustion per CH2 group of cyclopentane, cyclohexane and higher cycloalkane differ only very slightly from that of open chain alkanes. This implies that cyclopentane and higher ring alkanes are nearly as stable as open chain alkane. This obviously gives against Bayer strain theory, according to which cycloalkanes have more than 5 carbon atom rings should be increasingly less stable due to increasing deviation from the normal tetrahedral angle. Sachs-Mohr theory of stainless rings. To explain as to why cycloalkanes having ring of 6 or more carbon atom are almost as stable as a cyclopentane, 1890 put forth a theory of stainless ring for higher ring compounds. According to him, carbon atom consisting the ring lies in the same plane only up to 5-membered ring, while the carbon atom in 6-membered and higher rings do not lie in the same plane. Since the carbon atom in a six-membered and higher ring lies in different planes, the normal tetrahedral angle remains unaltered. As such, there is no angle strain in a bigger ring, and that is why they are stable. For instance, Sachs proposed the existence of two types of multiplanar and puckered stainless rings known as chair or boat forms of cyclohexane. Both these forms are free from angle strain and can be interconverted just by rotation around single bond. Thus, they merely represent two conformation of cyclohexane and cannot be isolated separately. Here, the chain form and the boat form are shown in this figure. Figure 4.5 shows the stainless rings of cyclohexane. Similarly, seven-membered and higher rings are stainless in nature. Sachs' theory of stainless ring was further supposed and elaborated by Mohr 1918 to cover the compound containing two rings fused together. Difficulty encountered in the synthesis of large membered ring. It may be interesting to know that as why bigger rings are rather difficult to synthesize even though there are no angle strain in them. This is primarily due to the fact that the two ends of the chain of atom must come close together for ring closure to take place through interaction between the groups present at the two ends. If the chain undergoes ring closure is very long, there are relatively lesser chances of the two ends come close enough for the ring to be formed. On the other hand, when what may happen is that the end of one chain may interact with the end of a different chain, leading to the formation of entirely different product. This difficulty is now being overcome by carrying out ring closure reaction in highly dilute solution. Under these conditions, collision between different chain are minimized and the ring closure takes place as the main reaction, although at a very slow rate. But once the rings are formed, they are quite stable. Bent or banana bond in cyclopropane orbital picture of angle strain. According to orbital concept of covalency, a covalent bond can be formed between two atoms only if these atoms are oriented in such a way that their orbitals can overlap each other. It may also be recalled that the greater the overlapping of atomic orbital, the stronger the bond formed. Now the carbon atom of cycloalkanes are in a state of sp3 hybridization, and formation of a covalent bond between two such atoms involve the overlapping of an sp3 orbital of one carbon with a similar orbital of the other. For maximum overlap, the bonding should take place in such a way that bonding orbitals point directly towards each other. Consequently, when carbon is bonded to two other carbon atoms, the CCC bond angle should be 109 degree 28 second. But in cyclopropane, the CCC bond angle is only 60 degree. This means that in cyclopropane, the bonding orbitals are not pointing directly towards each other along a straight line. As a result, the overlapping of these orbitals takes place to a very small extent, and bond formed are described as bent bonds. These bonds are much weaker than the normal carbon-carbon bonds. Consequently, the cyclopropane molecule is quite unstable or strained and reactive in nature. Here in figure 4.6, the first show maximum overlapping of sp3 orbitals of carbon in open chain or large ring compounds. B show poor overlapping of sp3 orbital of carbon in cyclopropane ring. Only the orbital concerned in bond formation shown. In cyclobutane, carbon-carbon-carbon angle is equal to 90°. The overlapping is relatively more effective than in cyclopropane, as such cyclobutane is relatively more stable. So our cycloalkane topic is completed. Thank you.